In this video, we're going to continue to talk about motion and representing motion with graphs, but this time we're going to talk about graphs of velocity versus time. In the last video, we showed how to represent the motion of an object using a position time graph, which just kept track of how far away an object was from the motion detector. And so we saw, for instance, an object could travel relatively slowly or an object could travel relatively quickly. And the difference on the graphs was the slope. So in the top graph, notice that this object only got 2 meters in 10 seconds. Whereas in the bottom graph, this object got 4 meters in 4 seconds. So that clearly this guy down here went faster than this guy. And we notice the difference is on this graph the slope is greater than the slope is here. And this led us to say that on a position time graph the slope is related to the speed. Another thing we learned in the last video is that slopes could be positive or negative. That I could also have a position time graph with a line that looks like that. And that would represent somebody who started far away from the motion detector and walked towards it. This line represented somebody who started near the motion detector and walked away. So this slope in math we recognized would be negative, and this slope is positive. So if slope is speed or velocity, I can have positive slopes and I can have negative slopes connecting to walking away from the detector or walking towards the detector. Let's look at a velocity time graph now. So here's our old familiar position graph, and on a position graph you have just how far away you are from the motion detector at what time. In a velocity time graph, first of all notice the zero line is in the middle of the graph so that I can have negative velocities and I can have positive velocities. And as you saw in the lab, the positive velocities are for when I'm walking away from the motion detector, so that the slope of the position time graph is positive when I walk away, so that gives positive velocities. And I can have negative velocities. So when I walk towards the detector on a position time graph, the line slopes downward, a negative slope, so that velocity would be negative. So let's say I walk away from the motion detector and I travel 2 meters in 4 seconds. But I walk very steadily, so my line looks like that. So I've covered 2 meters in 4 seconds. And let's figure out now, what would the velocity time graph look like for that? Well, this graph, the key to understanding this is realizing this graph doesn't care where you are. It now is going to graph how fast you're moving. So how fast I'm moving is represented by the slope of this. I went 2 meters in 4 seconds. So I would write down the slope, which is my speed, is rise over run, or change in the y-axis over change in the x-axis. So the y-axis, I changed 2 meters. So I went 2 meters, and I did that in 4 seconds. So delta y was 2 meters, delta x is 4 seconds. So the slope is 0.5 meters per second. So just like I divide 2 by 4 to get 0.5, I divide m by s to get meters per second. So that's actually my speed. Now the way I would graph that on a velocity time graph is to first of all realize that there is only one slope here. My slope is 0.5 here, and it's 0.5 here because it's a straight line. So my velocity is the same all the time, and it's positive, and it's 0.5 meters per second. So what I'm going to do is first of all find 0.5 and the velocity, positive 0.5, and it lasted for 4 seconds, so I draw a horizontal line at 0.5 for 4 seconds. So this graph and this graph are graphs of exactly the same motion. And we can also see that this graph is a graph of the slope of that graph, because velocity is the rate that the position is changing with time. Or as we saw before, the slope of this graph is speed, or velocity, and that's what we graphed. What do you think that it means that this line is completely horizontal? Well, on a graph, any line that's horizontal means whatever you're graphing is not changing. It's always the same value. Every second, the velocity is 0.5. So that means I have a constant velocity. What would it mean, do you think, if this line started to go up? That would mean that my velocity is changing. Now to practice doing this again, let's make them go faster. So whereas before, in 4 seconds, I only went 2 meters, now what we're going to do is we're going to make them go 4 meters in 4 seconds. So let's see what the velocity time graph would look like for that. So let's first of all calculate the slope. So the slope, which is the speed, is going to equal how much the y-axis changes divided by how much the x-axis changes. So the y-axis in this case now changes 4 full seconds, 4 meters, I'm sorry, and it changes 4 meters in 4 seconds. So now the slope is 1 meter per second, which happens to also be the speed. So now to do this graph, I find 1 meter per second velocity, and again, the slope is the same here as here. I'm moving at a constant speed, therefore I'm going to draw a horizontal line, or close to it, for 4 seconds. So again, a horizontal line here means I'm moving at a constant speed. A straight line here means I'm moving at a constant speed. The velocity time graph is a graph of the slope of the position time graph. Now what if we get a problem like this, where they say, here's a velocity time graph, now draw the position time graph that goes with it. So I would begin by asking myself, what does this mean? And I would say, well, it's a velocity graph, so this line tells me what my velocity is. So I'm going to look it up here. It's about half a meter per second. So I would say I have a speed of 0.5 meters per second, and I'm going to do that for 8 seconds. So the position time graph, though, is going to tell me where I am while I'm doing this. So at the start, I'm going to start at the origin, so I'm going to start right here. But how far will I have gotten in 8 seconds if I'm going 0.5 meters per second? 0.5 meters per second means every second you go half a meter. So I could ask myself, well, if I'm going half a meter every second, how far will I get in 8 seconds? So what I might do is say, I'm going to go 0.5 meters per second times 8 seconds. And if I do that, I can see the seconds are going to cancel out. I'll have 8 times 0.5, which is 4 meters. So if you only go half a meter every second, it's going to take you 2 seconds to go 1 meter. So every 2 seconds I'll go 1 meter. So if I'm traveling for 8 total seconds, I'm going to get to 4 meters. So what I'm going to do here is look up, here's 8 seconds, and here's 4 meters. So I'm actually going to get there. So that is going to be my position time graph. The slope of this graph is 0.5. You go up 4 on the y and you go up 8 on the x. It's a slope of 0.5. And so this graph told me I was moving at a constant speed of 0.5. So a position time graph means I'm getting farther and farther away. The reason this graph is horizontal means this is a graph of my velocity, and my velocity never changes. This is a graph of my position, and my position does change. My position increases half a meter every second. That's my velocity. So my position is getting farther away from the motion detector half a meter every second. So after 2 seconds, I will be 1 meter away, and after 8 seconds, I will be 4 meters away. So this graph and this graph depict exactly the same motion. What if we were given a problem like this? Draw both position time and velocity time graphs for this situation. Walk 1 meter per second for 4 seconds, and then stop. Well, let's take them one at a time. Let's do the velocity time graph first. So it tells us that we need to walk 1 meter per second, constant speed, for a time of 4 seconds. So to do that, on my velocity graph, I'm going to find positive 1 meter per second. And I'm going to find, here's 4 seconds right here. So let's draw 1 meter per second for 4 seconds. And then it says we have to stop. So the question would be, what is your velocity when you're stopped? So if you think about it, well, your velocity is 0. You're not moving. So on a velocity time graph, 0 velocity is right in the middle here. So my velocity drops down to 0, and then I've stopped. So this is a graph of moving at 1 meter per second for 4 seconds and then stopping. Now let's see what this would mean for a position time graph. So let me think this out. I'm going to walk 1 meter per second for 4 seconds. So I'm going to start out right here at 0, and then after 1 second I will have gone 1 meter. So 1 second, 1 meter. After 2 seconds, I will have gone 2 meters. After 3 seconds, I will have gone 3 meters. And then after 4 seconds, I will have gone 4 meters. So if I draw the line, it will look something like this. So after 4 seconds, where am I? I am 4 meters away from where I started. But then it says I stop. So what does that mean on this graph? What stopped means on this graph is you stay 4 meters away. So stopping means I stay right at 4 meters. Now it's really important to see here, first of all, how different these two graphs look, but they are describing exactly the same situation. So it's really important for us to understand what the graphs are telling us, because these two different pictures are describing the same thing. But the only difference between them is this is paying attention to where the person is, and this is paying attention to how fast they're going. So walking 1 meter per second for 4 seconds, well, if I'm walking away from the motion detector, then I noticed I starting right by the motion detector, so after 1 second I'm at 1 meter, after 2 seconds I'm at 2 meters, after 3 seconds I'm at 3 meters, and after 4 seconds I'm at 4 meters. That's what it means to walk 1 meter every second. So I'm moving 1 meter farther away every second. So I'm going to end up after 4 seconds to be 4 meters away. Stopping means staying in the same position. So it's a horizontal line there. Now, if I pay attention to how fast I'm moving, not where I am, it says walk at 1 meter per second. So I keep a steady 1 meter per second. My velocity is 1 meter per second the whole time I'm walking. This line only has one slope. This is that slope. Stopping means having no velocity. So I walk at 1 meter per second for 4 seconds and then stopping, which is velocity of 0. So also I could notice that velocity or speed is the slope of a position time graph. So this line has one slope, and that slope is 1 meter per second. So I graph one constant number, which is the slope of this line. And then the velocity is 0 here because the slope of this line, the position time graph line, that slope is 0. So this graph is the slopes of this graph. This graph has two straight lines. One has a slope of 1, the other one has a slope of 0. So if this graph is a graph of slopes, I have a slope of 1, slope of 0. In this question, I am already given a position time graph, and I am asked to draw the velocity time graph that goes with it. So first of all, let's describe what exactly is going on in this graph that would draw it like this. So first of all, I have a straight line starting from 0, straight line of increasing position that goes up to 4 meters and then comes right back down. So let's see, to make this line, I would walk away from the detector at a steady speed, and that speed would be found by taking the slope. So let's look at the slope here. I start at 0 and I end up at 4 meters. So I cover 4 meters of distance in 4 seconds. So this is a slope of positive 1 meter per second. And then at 4 meters, what happens? Well, the position starts to decrease. So what does that mean? It means that my distance from the detector is getting less and less, which is just a fancy way of saying I'm walking towards the detector. So being back here means I'm actually back at the detector. So I've actually reached the detector again at 8 seconds. So I walked away from the detector for 4 seconds and got 4 meters away, and then I turned around and I came back walking at a steady speed till at 8 seconds I got back to where I started. So this could be a graph of somebody walking down a 4 meter long hallway, or walking 4 meters down a hallway, and you walked in a straight line at 1 meter per second, and then at 4 meters you turned around and came back and walked exactly on the same line till at 8 seconds you were back where you started. So the speed here, notice this is a negative slope. So I'm actually covering, let's see, I go the same 4 meters and I do it in another 4 seconds. So I actually have a speed of, or velocity of negative 1 meters per second. So that, talking my way through this, helps me draw this graph. So let's draw this graph. So for the first 4 seconds, I go 1 meter per second. And then for the last 4 seconds, I go negative 1 meter per second, because the slope here is negative. And I can just assume here that, according to this graph, I did a super amazingly instant turning around. So I can represent that here just with a vertical line. Notice again how different these two graphs look, but they're actually describing the same thing. This graph says you walk down the hallway, so your distance from the motion detector increased at a rate of 1 meter every second, and then your distance from the motion detector, because you turned around, decreased at a rate of 1 meter every second until you got back to the start. This graph says you walked away, because it's positive, at a rate of 1 meter per second, which you were steady. So this straight line indicates I'm walking at a steady speed. On a velocity graph, this horizontal line means I walked at a steady velocity. And then this here means you turned around, and I'm walking backwards at a rate of negative 1 meters per second. Last question. What kind of motion would this be a graph for? Think about it.